I'm looking at analogies between fluid dynamics and biology and chemistry. Helicity, which is link, twist, and writhe, if you look at it topologically, is related to DNA supercoiling in molecular biology. Vortex reconnection is related to DNA site-specific recombination. And Gross-Pitiev isosurface, which is one of the models you can look at and doing simulations of vortex dynamics, are related to the Belousov-Zhabotinsky waves of excitation in an excitable medium. So the idea is to take things that work here and see if they'll work over here, and some of them do. And hopefully one of these days to take some of the things, the mathematical techniques that work here, and use them in this arena as well. So here's a picture of vortex reconnection for a pair of trailing contrails from a 2-engine jet plane. So you can see the things reconnecting and spitting out little circles. Vortex reconnection is very important in solar physics because you have solar flares, which is a reconnection of these magnetic field lines. You'll get a reconnection here and it'll spit out a circle that comes toward the Earth and gives us problems. So here is anti-parallel flux tube reconnection. So I've got a flux tube here. So the one on top, beta, is rotating by the right-hand rule like this, and the one on the bottom is rotating in the opposite direction. These things come together in this anti-parallel fashion, creating this sort of intermediate here, and then it reconnects like this. Same thing happens in DNA. So this is duplex DNA. You can think of the red as Crick and the blue as Watson. And you sort of have a reconnection event where the red reconnects with itself first, the first strand, and then the other strand reconnects. So we have this strand and this strand reconnecting to this one and that one. So a little bit of topology. Topological entanglement. Well, you can have writhing like a telephone cord. This is a geometric measure of non-planarity. Here's a writhing of a linear thing, and here's a writhing in a circle. You can have knotting of linear things or knotting of circular things. You can have linking of linear things and linking of circular things. So this is the kind of thing, entanglement. And you can measure entanglement in circles anyway by measuring the crossing number. So you sort of take a configuration in 3 space. These are all elastic. And you reduce it so that in the projection here you have the minimum number of crossings. 0 crossings, 2 crossings, this is the Hopf link, 3 crossings in this trefoil knot. So the crossing number is a measure of topological entanglement or topological complexity. Turns out that Mother Nature hates entanglement. In DNA, entanglement of a plasmid in a bacterium will block replication, transcription, cause mutation, leads to cell death. So it's a bad thing that Mother Nature has to fix continually. Cellular processes produce DNA entanglement because DNA is wound up like this in the Crick-Watson helical structure. Vortex entanglement blocks energy dissipation. At least I think so. I mean, there may be people that know more about this than I do, so they'll tell me if I'm wrong. But Mother Nature always finds a way to eliminate all entanglement, especially in biology. And the problem is, how does Mother Nature do this? Because, well, there are proteins in the cell called topoisomerases that DNA uses to manufacture a place where the DNA can pass through itself by binding to one strand of DNA, breaking it, holding on to the ends, passing the other one through, sticking them back together. So by strand passage mediated by a protein, you'll change a crossing from over to under. And it turns out that DNA site-specific recombination can solve entanglement problems, as you'll see a little bit later in this talk. And vortex reconnection, as you'll see, reduces entanglement. The problem is that entanglement is a global property, and all these moves to fix it are local. So the problem is, how does Mother Nature know how to fix it? Because you could do the wrong thing and make it worse instead of better. So the answer to this is, even in biology, it's a subject of a lot of argument about how Mother Nature fixes it, statistically or somehow, but it's got to fix it, because otherwise, if you've got entanglement in the cell's going to die. So the question is, how can local action solve global problems? And people really don't know. But here's a very interesting piece of work done in Bill Irvine's lab at the University of Chicago in 2013. People for 100 years or so have been wanting to make knotted vortices, and these guys actually did it. So they produce hydrofoils like this with a 3D printer. You coat the hydrofoil with little bubbles, put it in a water bath, and pull it. It spits out, as you see here, a circular vortex ring. And you can visualize the center line of the vortex. That's the low pressure, so the bubbles go to the center line, and you can watch this thing migrate through the fluid. This one, the unknot is very stable. It's a planar unknot. It's this one, though, the trefoil knot, that reconnects with itself fairly quickly. So let's see if I can play the movie here. Ah! So here you see the Hopf ring. These are two circles linked like this, and they're going to reconnect. And anytime you got a reconnection event, if you've got two circles reconnecting, they become one circle. If you've got one circle reconnecting with itself, it becomes two. So the topology always changes. So they're rotating it around with this sheet laser to do the visualization here. And you'll see a reconnection. I think it happens sort of right here. It's reconnecting now. Boom, it's now reconnected, and now you've got a single big circle from the Hopf link. That's unknotted, by the way. And these two circles, this single circle will now reconnect with itself there, becoming now two unknotted circles, unlinked. So we had the Hopf link becoming one big circle, reconnecting again to become two unknotted, unlinked single circles. Here's the trefoil, the really interesting one. And it's going to reconnect in an anti-parallel fashion right here. So this is a close-up with slow motion here. You'll see this thing reconnecting. Bam, it's reconnecting now. And after reconnection, the trefoil knot becomes the Hopf link. It's sort of hard to see, but that's what this is. And then it kind of dissipates. Then the Hopf link reconnects. If you were to run it completely, trefoil reconnects to the Hopf link, which reconnects to a single unknotted big circle, which reconnects to two small unlinked unknotted circles. Very interesting topological decrease in complexity mediated by reconnection. So the picture from, if you take some still frames from that video, so here they are redrawn, and you can sort of see the reconnection happening here. So it's anti-parallel vortex reconnection. Here's a crude diagram to show you the reconnection cascade, starting with the trefoil, and it reconnects here. You can think of this maybe as a band, where you have these two edges in the band are switched for the other two edges. So you have one reconnection event that produces the Hopf link here. You have another reconnection event here that produces a big unknotted circle. You have another reconnection event that produces two unlinked unknotted circles. Here I've drawn this sort of, I've simplified these drawings to get rid of these topologically trivial things. These have Rive, but you can sort of get rid of these. Rademeister 1 moves. Well, here's the biology. It's a very interesting biology experiment that discovered that site-specific recombination can solve this topological entanglement problem. So this is a plasmid that's been reproduced in a cell, but the trouble is that the two daughter molecules here are linked with each other in this right-handed toroidal fashion. It's right-handed because the Crick-Watson structure is right-handed. So this is kind of an end of replication, but the cell needs to, you have two daughter cells, and you want the yellow one to go into one cell, the blue one to go into another cell. So the problem is, how does Mother Nature fix this to make it like that? And it turns out it does a stepwise reduction in topological complexity by means of site-specific recombination. You have this torus link of 6 crossings becomes this torus knot of 5 crossings, becomes this torus link of 4 crossings, becomes this torus knot of 3 crossings. Now this is the same one you saw in the fluid experiment. And from here on down, it's the same as, identical topologically to the fluid dynamics experiment. Trefoil goes to Hopf link, goes to big circle, goes to 2 unknotted, unlinked small circles. So, Reconnection questions. You'd like to get detailed dynamics and discover something about helicity. So helicity is a measure of knotting and linking of magnetic field lines, if you like, and it's a lower bound for energy. The question is, what are these things that reconnection preserves? It certainly does not preserve the topology, so it has to preserve other kinds of things, and one of them that it conserves is helicity. I'll show you that it's conserved. Rive helicity is conserved under anti-parallel reconnection. And another thing would be to understand the reconnection cascade. Why is it going down like this in topological complexity? Presumably that's energy talking, but the energy is not really that well understood. So I'm now going to do a bit of mathematics to discover or to elucidate the rive. So if you have two oriented skew lines, straight lines in space, you can look at a projection of these lines. And if you see a crossing, you can assign a plus or minus to it. So this is a plus crossing, and this is, if you change the orientation of one of the two strings, it changes the sign of the crossing. Or if you take the mirror image, it changes the sign. So it's a signed crossing number by sort of a right-hand rule. And to compute the rive of a circle in space, you think of the circle as being rigid, and you take a projection of it, compute the signed crossing number, you sort of add up all the signs, then you rotate it a little bit, compute it again. So you simply average this integer number over all projections. And this gives you a real number, and it's called the rive. It's a measure of non-planarity. If you have something that's really wound up, it has high rive. So to average, the rive is the average of the sum of the signed crossings over the space of all projections, which is the unit 2 sphere in R3. So here's a DNA, an electron micrograph of DNA. This is with relaxed, and this is where the riving goes up, and this is a highly supercoiled DNA circle. So I'm going to assume everything consists of the piecewise linear curves. So I have little straight segments on my curves. And I'm going to compute the rive and compute the linking number by looking at pairs of edges. So if I've got two edges, EI and EJ, I can compute the signed area on the unit sphere. That's the space of all projections, covered by direction vectors where you actually see a crossing. You know, a lot of the time you won't see anything, but if you do see a crossing, you'll have a fixed sign, and so that'll give you an open set on the 2 sphere that you can assign a signed area, with the sign being the sign of the crossing. And antipodally, since if you look at it this way, it's the same as looking at it this way. You'll have a pair of antipodal open sets, and you just add up the areas, and it's got this sign, in this case, a plus sign. So that gives you a value. It's the signed area covered by signs, crossings, directions where you see a crossing for these two edges. So you can compute the rive of an oriented polygon like so. You have n edges. The rive is you average, so 1 over 4 pi. 4 pi is the area of the unit 2 sphere. And you can simply look at every edge AI against every other edge AJ. So that's the rive of a simple closed curve. Linking number is essentially the same. If you take two disjoint-oriented polygons, one with n edges, one with m edges, A and B, the linking number is simply the same sort of average where you sort of look at the edges in A versus the edges in B and add them all up. So this one is an integer. The previous one is a real number, so it's not necessarily an integer. But here's the most interesting equation, and it's the rive of the union of two disjoint closed curves. So the rive of A union B is, well, you look at the edges in A versus the edges in A, plus the edges in A versus the edges in B, plus the edges in B versus the edges in A, plus the edges in B versus the edges in B. So the rive of A union B is the rive of A plus 2 times the linking number. This is the linking number of A and B. This is the linking number of B and A, which happens to be equal to each other, linking symmetric in the 3 sphere. And this is the rive of B. So you get this formula for the rive of the union of disjoint union of 2 circles. And here I'm going to think about reconnection by looking at an intermediate. Here I've got 2 circles to start with. In this picture, they're not linked. They could be. It doesn't matter. It's just easier to draw it when they aren't. And what I'm going to do is I'm going to take A and B, and I'm going to assume that A has an edge like this and B has an edge like that, and I'm going to superimpose those edges by translation. So I'm thinking of these now as rigid. And I'm going to move A and B together to give me this intermediate, this theta curve intermediate. And then I'm going to erase the interior of this common edge here, and this now produces the reconnected curve. So these two curves reconnect via this theta curve intermediate to produce the reconnected guy. So I'm going to remove the interior to get this reconnection, and now I'm going to compute the writhe. I claim that the writhe of A union B is equal to the writhe of the theta curve intermediate. And that's because all these numbers are preserved by translation. I mean, translation preserves writhe of A, writhe of B, and it certainly preserves linking number because that's a topological invariant. So, in the writhe of the theta curve, I'm counting this common edge twice, once going up and once going down. But since they have opposite orientations, the writhe components cancel out. If both AN and BM are counted, these things are oriented oppositely and they cancel, so I get the writhe of the connected sum, or the reconnected curve. So this is a proof that antiparallel reconnection is writhe preserving. So if you've got a single curve reconnecting with itself, it's a little different. I mean, a single curve reconnects to form two curves. The writhe of the single curve changes, it approaches this limiting value, which is the writhe of the theta curve intermediate. And then this limiting value is equal to the writhe of the reconnected pair of curves. So now I'd like to talk a little bit about helicity. Now, with helicity, I'm going to think of myself as a situation where I've got vortex tubes. Everything's happening inside of these tubes. The tubes may be linked and knotted, but in a single tube, if you take the center line here and look at one of the field lines here, you get a ribbon. So if you like, this ribbon describes the framing of this curve C gamma here. And so this, if you push off along this ribbon, it gives you this companion, which is then, I should label this C gamma prime. It's linked with C gamma, and the linking number itself is the framing. Given a ribbon like this, you can compute the twist of the ribbon. So this is one that Calaguriano and White did to look at DNA, Fuller. And the idea is you take a vector that goes from your center line here out to the edge, and then you can get yourself a triad here, and you look at the incremental twist as you go along the ribbon just a little bit, and you integrate this guy, giving you this real number. And it turns out that the linking number of the black one and the red one is equal to the sum of the writhe of the center line plus the twist of this ribbon. So that's the famous link equal twist plus writhe formula that allows you to figure out what gel electrophoresis does to circles in molecular biology. It's very important in molecular biology. So this is now the integral version of helicity. So you've got a divergence-free vector field. You have this vector potential A. Del cross A is B, the field that you're looking at. And it has compact support on domain D, but it's confined to knotted and linked tubes in D. You know, we're going to just get down to some topology here. Yeah. So the helicity is this integral, and it's a measure of twisting, knotting, and linking of field lines. And the absolute value of this thing, it's a signed quantity, is a lower bound to the energy of the vector field. But fortunately, Keith Moffat and Renzo Riga fixed this for me because they converted helicity as an integral. I can't compute integrals anyway. And the idea is to convert it to topology, knotting and linking. Thank you, thank you. So if you've got a flux tube with center line C gamma and flux ribbon R gamma and flux phi, the flux ribbon boundary is the union of these two guys, the center line at the edge of the ribbon. The helicity is phi squared times the self-linking number here. And the self-linking number of that flux tube is the writhe of the center line plus the twist of the ribbon. And, you know, it's a theorem that this number is actually equal to the linking number, and it's a topological invariance, so it's preserved under diffeomorphism. If you have space kind of moving and itself flowing, that's why this thing is an invariant. So now we're going to reconnect two tubes of the same flux, so we're going to assume that phi is equal to 1 for this calculation. So the helicity of the union of two flux tubes with the same flux here, again by Moffat and Rica, the helicity of the union of two flux tubes is the self-linking number of alpha plus the self-linking number of beta plus 2 times the linking number. And it's this formula right here that got me into this trade, because I showed you a formula for the ride, A union B, and it has 2 times the linking number. I went to a talk one time in this subject. I saw this equation, didn't understand a thing except the number 2 here. It's 2 times the linking number, that's the key. So that's how I got into this trade. So the self-linking number of alpha, there it is, twist plus ride, twist plus ride, the beta, 2 times the linking number. And you can write it like this, as the writhe helicity, which is the writhe, one writhe of the other, 2 times the linking number, that's the writhe thing, and then the twist helicity here. So it's writhe helicity plus twist helicity, and I also gave you a proof that with anti-parallel reconnection, writhe helicity is constant, it's unchanged, so it's invariant under anti-parallel reconnection of vortices. Blah, blah, same thing over again. You can apply this to places where you really don't have any ribbons, so there's no twist. So if you've got an empty flux tube like optical vortices and maybe superfluid helium, the helicity is, instead of the twist, you replace it with a torsion of the center line, so there's no ribbon to talk about. So again, that's the result of Moffat and Rica. The helicity is conserved under anti-parallel reconnection, since the writhe and the torsion add correctly. You can also look at superfluid helium. This is a very interesting situation where you have a vortex tangle. So this is sort of quantum turbulence. And they do simulations. Carlo Berenghi has simulations of this thing where you start with a bunch of circles and then you reconnect them like mad and try to look at the topology on the average of what happens with a lot of reconnections of a topology or a confined, volumetric confined bunch of circles. You start with a bunch of unknotted, unlinked circles, and of course after some reconnection, they get all topologically screwed up. So it's a problem I'm interested in, and so what happens when you do some reconnection on one of these tangles? Well, this is a lot of closed curves, probably knotted and linked, and has very high writhe in general. So if you have anti-parallel reconnection, say the first 2 reconnects, and the rest of them don't, the following quantities, which you could call helicity, they're certainly related to it, are conserved by anti-parallel reconnection. 2 times the sum of the linking numbers plus the summations of the writhes of all these beasts. Or this same thing where you add on the torsion of all the center lines. So these quantities are conserved by anti-parallel reconnection in one of these tangles. I'd like to, as the final here, I'd like to talk about Seifert framed links and prove to you that you have 0 helicity. So I'll tell you what a Seifert framed link is. It has to do with Seifert surfaces. This result, in fact, has been recently proved by Hader Salomon. Who's Hader here today? He was here. There he is. Yes. And I gave a talk on this. There was a quantum turbulence conference in Tallahassee, and I thought I had a proof of something new. And I went to the conference, and first of all, Hader just sent me his paper. Whoa, he already proved it. But not only that, it had already been proved in 1992 by these Russian guys. But the problem with this proof is, I've tried to read it. I swear to God, I can't understand it. So I'll tell you, I'll give you the proof. I think this is the proof these guys were thinking of, but I'll give you a purely topological proof. No integrals, nowhere, which is for me a good thing. So what's the Gross-Pitievsky isosurface? Well, the GPE, the Gross-Pitievsky equation, is one that's used to do simulations of vortex dynamics, and it's pretty good. it does, you can make it do reconnections and you can sort of see what happens. And in the GPE, so I've got L of an oriented vortex length in R3. And I've got the complement here, the link complement, R3 minus L. So you take away these, so L is sort of the singularities of phase of GPE. And X is the complement. So the GPE gives you a phase map, a map from X to the unit circle here, S1. I take the base point star in S1. It's a regular point of this map. So I take the pullback and I get a smooth manifold V that's orientable and whose boundary is equal to L. So that's the Seifert surface for this oriented link. So this is standard sort of construction in knot theory. And I got onto this sort of thing by looking at the Belousov-Zhabotinsky reaction, so the real-time evolution. So this is a reaction diffusion system. These are pictures taken in a petri dish. It's a circular chemical reaction, and you have waves of excitation. So this is a wave front here. The really interesting ones are the wave fronts where you've got these counter-rotating sort of logarithmic spirals. And at the center point of these spiral waves, you have singularities. And the way to understand what a singularity is, it's very simple. So suppose you go to a football match. That's what they call it here, right? Football. Okay, so you've got like a bunch of people sitting around in the stands and they're doing the wave. Now suppose that the whole thing is full of people. You've got people down on the field, and you've got this one person standing right in the middle of the field. The wave is going around. As the wave progresses, just in front of the wave, you have an excitable medium, and a football crowd is an excitable medium if you've ever seen one. And just behind the wave, it's refractory. So if two of these waves were to run into each other head on, they would annihilate each other because it's refractory behind both of the waves. On the other hand, you've got this spiral wave going around. You have to have a singularity in the middle where this guy's standing, because everywhere he looks, people are waving. No matter when he waves, it's got to be wrong. So it can't be continuous. That's the two-dimensional version. You got the 3D version. Hello, yes, 3D. Where these points become circles, yes, knotted and linked circles. Of course, you can't do pictures of them, but you can write necessary and sufficient conditions for the existence of spiral wave patterns in 2 dimensions, in a petri dish, if you like, or in 3 dimensionals with sort of vortices that are knotted and linked. So given local information about what's happening at the singularities themselves, the framing, if you like, there are necessary and sufficient conditions on the framing that tell you whether or not there's a wave that connects them all up. They involve this Seifert framing. Okay, so here I've got the trefoil knot, and the blue thing is the Seifert surface, V. Now, if I take a push off of K on the Seifert surface, I get this companion, K prime. These two guys, K and K prime, co-bound a ribbon. So that's the ribbon going around the red guy. So that's the Seifert framing. K prime is the framing of K. And the boundary of V is equal to K. And if you take V prime, you can get V prime from V by simply erasing the interior of the ribbon, giving you the black boundary thing here. You get a surface V prime that does not intersect K at all. So the intersection of the red guy, K, and V prime, which is what you get by deleting the interior of the ribbon, is the empty set. So the intersection number is 0. You can compute linking by means of computing intersection numbers. So if you've got a cycle B here, which is the boundary V2, I don't know where. Anyway, the linking number of A and B is the intersection number of A with V2. So it's an integer. I claim now that the Seifert frame knot has a 0 helicity. Because if you've got a flux line with center line, suppose you've got a knot here. So you've got this single curve, this flux ribbon, and the boundary of the ribbon is that guy. The point is that the helicity is phi squared times the self-linking number, but the self-linking number is 0 because the linking number of these two guys is 0 because this one bounds a surface that this one misses. So that's a proof that the helicity of a single Seifert framed circle is 0. If you've got a bunch of them now, a link of n components, the same sort of calculation works. you have this Seifert surface V, so it's this orientable surface. The boundary of V is equal to this link. So all the components of the link co-bound this manifold, which may or may not be connected. That's not important. V intersects the boundaries of tubes around each of these, producing ribbons, and these ribbons have these companions or push-offs, giving you AI prime. For each AI, the Seifert framing is AI prime that gives you this little ribbon. You can delete the interiors of all the ribbons to get this surface V prime, and V prime doesn't hit any of the components of the original link. So the boundary of V prime is the union of all these sort of companion curves. And the link itself does not intersect the V prime. So the linking number of AI Aj is equal to the linking number of AI Aj prime. And this is true if you put primes or without primes for all I different from j. And the linking number of AI with AI prime, the self-linking number, is defined. And if you take Li prime to be AI prime, the push-off of AI union all the other components of the link, the linking number of AI with Li prime is equal to 0 because it's the self-linking number of AI plus the summation of these other linking numbers, and that's equal to 0 because this intersection number is 0. This equation is true for each I. So you've got these in sort of equations. So this is kind of a component of the helicity, if you like. And if you take this quantity here and add it up over I, as I goes from 1 to n, you get the helicity of the link. And it's 0 plus 0 plus 0 plus 0. So the interesting thing is that this condition, these inequations, is a necessary and sufficient condition for the existence of the Seifert surface. So given local information about the oriented link itself, information about the self-linking numbers of each of the ones, and the linking of the whole conglomerate, and if you've got this equation satisfied for each I, then there is a Seifert surface that spans the thing. So that local information can be parlayed into global information. And that's pure topology. So I will not do the proof. Anyway, so blah, 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 blah. I told you the proof here. Here's an interesting question that I don't know the answer to. That's one of many, I might add. So you can randomize a curve or a selection of a bunch of curves by means of random strand passage. That gives you, it randomizes an embedding, and you can sort of look at random knot types, random linking, and stuff like that. Now, every strand passage can be thought of as 2 reconnection events. One reconnection event, and then another one produces this strand passage. Certainly, strand passage randomizes topology. So the question is, how about reconnection? Does reconnection randomize topological complexity? Here's a reconnection giving you unlinked circles. Here's reconnection giving you the Hopf link. So I have no idea what the answer to this question is, and I guess what it's going to take is to do some statistical mechanics and some simulations. Anyway, the conclusions are that site-specific recombination and vortex reconnection have interesting similarities. Antiparallel vortex reconnection preserves Rye helicity. Seifert frame vortex links have 0 helicity, and thank you very much. A
couple of questions. Next speaker, please set it up.